welcome back. We're going to do a third video on double integrals. We're going to solve this problem here. Evaluate the integral of x times y with respect to area where R is a region in the first quadrant enclosed by the curves y equals the square root of x, y equals 6 minus x, and y equals 0. Got that region plotted down here below. Alright, so we've got the square root graph. Again, I did this in Maple. We could do this in graphing calculator or Desmos. Alright, y equals 0. Remember, that's the horizontal line passing through height y equals 0, which is the x-axis. Alright, so what are we talking about? The region R is enclosed in the first quadrant by these curves. This is our region R inside of those three curves. And let's take a look at that in Maple for a second, and what our options are going to be as to whether we're going to want to set this integral up as a type 1 integral or a type 2 integral. Alright, I've got that problem brought over. Alright, so there's the region that we know about. Now let's take a look at what the slices look like if we think about the vertical slices. And as we go across, notice we're stopping here and we're seeing that the bottom's staying the same. It's y equals 0. Alright, it's at height 0. But the top of this region will change as x goes past 4. So it's going to be the square root graph up to 4, and then it would be the graph of y equals 6 minus x. That would be the top of it when we go past 4. So we can set this up as a type 1 region. It's just going to have to be two separate integrals. One as x is varying from 0 to 4, the other one as x is varying from 4 to 6. So we can do that, all right, and we'll set that up that way. But we can also do this by looking at horizontal slices, or a x dy integral, thinking about this as a type 2 region. So for that, we're going to let y vary from the bottom to the top, and then consider what happens as x varies from the left-hand side to the right-hand side of our region. All right, and then that's how we'll solve the problem, but we'll set it up both ways just to get that experience. All right, so looking back over here, I've got this, and I'll use this graph here to set it up as a type 1 region. All right, so let me just erase the letter R there. And we're going to have to split this into two. All right, one region where x is between 0 and 4. So we're going to say, all right, fix for any x between 0 and 4. We're going to let y vary from the bottom of our region up to the top. The bottom is height 0. The top, in this case, is the square root of x. Okay, and then as x is going to vary between 4 and 6, we're going to let y vary from the bottom to the top again. The bottom is still y equals 0. The top has changed, though, to y equals 6 minus x. So if we want to do this as a type 1 integral, a dy dx integral, we got to set up two. One when x is varying from 0 to 6, and for each one of those x's, we're going to let y vary from 0 to the square root of x. And our integrand was x times y, then will be dy dx. Got to stop here, got to fix this. I might have said that wrong. Alright, but we're letting, for the first region, first part of this, we're going to let x vary from 0 to 4. Alright, and for each one of those x's, we're going to let y vary from 0 to the square root of x. And then as x is varying from 4 to 6, we need to then let y vary from the bottom, which is 0, to the top, which changed to y equals 6 minus x. And then we have x, y, dy dx. And that's fine. We can do it that way. It's not that hard of an integral to do it in terms of that. We just have two separate double integrals to evaluate, two separate iterated integrals. So that's fine. You can do it that way. All right. Let's see what it would look like if we set this up as a dx dy integral. For that, we would need to know, all right, what's the bottom and what's the top of our region? All right, well, it's pretty clear in the figure that it's from 0 to 4, or 0 to 2, pardon me. How do we get that? You would get that by taking the two curves, y equals the square root of x and y equals 6 minus x, and setting them equal to each other. All right, when we do that, we would then need to square both sides to get rid of the square root, and then solve the resulting equation. Whoops, when I square the square root, that goes away, because we get x on the left side. We have to square out that binomial, get 0 on one side, factor, use a quadratic formula, what have you. I'm not going to go through that, but you will get that x is equal 4 as one of the solutions to that. All right, and again, I'm going to skip over some of these details, but you would get that x is 4, and that would give you that y is 2 by plugging back into either one of the original equations. So we're going to say for any y between 0 and 2, I'm just going to put a generic 1 there. We're going to let x vary from the left-hand side to the right-hand side. Okay, and keep in mind that that's a horizontal variance, and it's varying as x is varying from the left-hand side to the right-hand side. Well, we were given before that the curve was y equals the square root of x. We need to know what x is in terms of y. So we need to take that equation and solve it for x. That's pretty easy to do, just square both sides. So we get x is equal to y squared. Alright, and now similar for the other curve on the other side. That's y equals 6 minus x. Oops, sorry. And then if you solve that equation, add x to both sides and subtract y, we would get x is equal to 6 minus y. So what are we going to say? We're going to let x vary from the left side to the right side. The left side, we're at y squared. Alright, for that fixed y value, x is equal to y squared. And then the right-hand side is 6 minus y. Alright, so let's finish this up by setting the double integral up and then evaluating it. Alright, so our double integral is going to look like this. We've got the double integral over our region of x times y with respect to area. Alright, and then we're going to end up with a dx dy integral for this one. Alright, and what we said was we're going to let y vary from 0 up to 2. For each one of those y values, we're going to let x vary from the left side, which is y squared. The left side is the smaller x value, up to the larger x value, which is the right side, which is 6 minus y. And then we get x, y, and this time it's going to be dx dy. Alright, and now we just need to go through and evaluate this iterated integral. So we need to find the antiderivative or the anti-partial derivative with respect to x, and then use the fundamental theorem of calculus to evaluate that inside integral. So again, we still got the outside integral will stay the same. Looking at our inside, looking at our function we need to integrate here, our integrand, we've got x times y. We're going to treat y as a constant with respect to x. And again, remember, constant factors come along for the ride in doing derivatives and antiderivatives. So we're just going to leave the y there. The antiderivative of x is 1/2 x squared. And again, that constant factor of y is just going to come along for the ride here. And then we need to take that and evaluate it by plugging in x equals 6 minus y and plugging in x equals y squared wherever we see x. And then we have to take the resulting integral and evaluate that with respect to y. Okay, so let's carefully plug in and continue this evaluation. So what do we have here? I'm going to leave the 1/2 out in front. I'm going to leave the factor of y off to the right side. X is being squared, so we need to do a difference of these squares. We've got to plug in for x and then subtract. All right, what are we plugging in? We're plugging 6 minus y in for x, and then separately y squared in for x. And then that is now an integral involving only one variable, in this case the variable y, which we will work out. Okay, so we've got a little bit of algebra to do here. The 1/2 we can bring outside the integral. We need to square this binomial out in the first term. So this first term is 6 minus y times 6 minus y. When you distribute each term to each term, multiply it out, you end up getting 36 minus 12y plus y squared. Okay, yep, then we've got the y on the outside. I almost forgot about that y that's sitting on the outside. We'll leave that out there for now. And then we're going to have minus. Now this term here, when we take a base to a power to the power, we need to multiply our exponents. So we get y to the 4th power. And then we can't forget about that other y that's outside of the parentheses. So now we need to distribute that factor of y through the parentheses, and then we'll just integrate simply term by term. So we have as our simplified result 36y minus 12y squared plus y cubed minus y to the 5th power dy. And then it's just a simple matter of integrating term by term. and then finalizing it. Alright, so just a little bit of plug and chug work to do from here. So we get, as an antiderivative, 36 times 1/2 y squared minus 12 times 1/3 y cubed, right? Increase the, reversing the power rule here, increasing the power, increasing the exponent, and then multiplying by the reciprocal of that exponent, dividing by that new exponent. 1/4 y to the 4th minus 1/6 y to the 6th power. And then we need to evaluate by plugging in 2 for y and then 0 for y. Whenever we plug in 2, or plug in 0, it's going to cancel everything out, so there's nothing to do there. Alright, I'm going to simplify this a little bit as we do the plug in. 36 times 1/2 is 18. We're going to get 18 times 2 squared minus 12 times 1/3 is 4. And we got to cube it, plus 1/4, and then we got to raise it to the 4th power, minus 1/6 raised to the 6th power. Alright, now we're plugging in 2 everywhere. And then we would also have to plug in 0 everywhere, and then subtract that result off, but clearly that's going to make everything 0, so I'm not even going to bother writing that. And then we just need to clean this up. So we get 1/2 times, we're going to have 18 times 4, which is 72, minus 4 times 8, which is 32, plus, we're going to have, let's just write these next couple out, 1/4 times 16, minus 1/6 times 64. 2 to the 6th power is 64. Alright, and the rest of that's just to clean up. Okay, I'm not going to spend any more time, but you can pause the video and go through and check the adding and subtracting these quantities here on the inside and working with the fractions. You get 1/2 times 100 over 3, and if you simplify, 2 goes into 150 times. So the final answer will come out to 50 over 3. Alright, now that's way further up here. So what did we end up getting? We had the integral from 0 to 2, the integral from y squared to 6 minus y of x times y, and then we did that dx dy. That was what the double integral that we had the choice to evaluate, and that comes out to 50 over 3. And that's it for this video.